Alright, Assalamualaikum, ladies and gentlemen. Let's continue our discussion to question number 4 for the past year's question, February 2025. The question states that a gas turbine power plant operates on the ideal Brayton cycle between the pressure limits of 100 kilopascal and 800 kilopascal. Air with a mass flow rate of 150 kg per second enters the compressor at 303 Kelvin and leaves at 603 Kelvin. The maximum temperature in the cycle is 1400 Kelvin. During the operation, the net of power is measured to be 45 megawatt. For this operation, the changes in kinetic and potential energies are negligible. They require you to sketch the cycle on a single TS diagram and also to determine all these items. A is the actual and ideal compressor power input in kilowatt. B, the isentropic efficiencies of the compressor and turbine in percentage. C, the thermal efficiency of the cycle in percentage, and also they requires you to determine the new thermal efficiency in percentage if an ideal regenerator with 100% effectiveness is added to the plant. So given to you here is all the necessary properties such as the specific heat capacity at constant pressure, constant volume, the specific gas constant, and also the specific ratio for your analysis. Alright, so like I said previously, the first thing that you need to do once you receive the question is you need to read and really understand what has been given to you. So from this question, we know that the pressure, the operating pressure is in between 100 and also 800 kilopascal. So if we look into the TS diagram for the ideal Brayton cycle or simple Brayton cycle, we will have this kind of TS diagram. Okay, so do not forget, once you are required to draw the TS diagram, to sketch the TS diagram, please remember that you need to have the axis, you need to have the title, you need to have the arrow, the states, the numbering. So then you are going to get marks on that. Okay, so now we can see that in this TS diagram, pressure at state 1 and 4 will be the same. Similar to pressure at state 2 and 3 will be the same, which is 800 kilopascal. For 1 and 4 will be 100 kilopascal. Alright, so next, what has been given from this question is the mass flow rate m dot 150 kilogram per second. So given to you here is the temperature of the air entering and also leaving the compressor. Okay, so from this question, once it's give you the pressure and also the temperature, most likely the temperature given here is the actual temperature leaving the compressor. So when you do the listing for the item that is being given from the question, so you're going to get T1 is 303 Kelvin and T2A will be 603 Kelvin. Okay, from the question also it gives you the maximum temperature of this cycle, which is 1400 Kelvin, so that will be the temperature at state 3. If you look at this TS diagram, also you can notice that state 3 will obtain or will have the highest temperature amongst the other states of this simple Brayton cycle. And lastly, that is given to you is this power net out 45 megawatt. This also actually the actual net power that has been produced by this cycle. Alright, so the first question requires you to find the actual and also the ideal compressor power input. So the power input is being given by this relation. The top one is referring to the ideal power input by the compressor, and the bottom one is the actual power input by this compressor. Alright, so since you have the temperature for state 2, the actual temperature at state 2, T2A, and also you have the temperature at state 1, Cp has been given by the question. And then the mass flow rate also has been given by the question. Now you can determine the actual power input by the compressor. So you're going to get the value of 45,225 kilowatt. Alright, so next is for you to determine the ideal power input by the compressor. So in order to determine the ideal power input by the compressor, you already have the Cp, you already have the m dot, you already have the T1, but you need to find what is T2S. So T2S can be determined using this isentropic relation, T2S over T1 equal to P2 over P1, power of K minus 1 divided with K. So if you forgot about this formula, this relation, you can always refer to your appendix that will be given in your final examination. So once you obtain the T2S from this relation, then you can substitute that value to determine the power input, the ideal power input by the compressor, and you will get this value. Right, so now you have the actual power input and also the ideal power input by the compressor. Okay, next, they requires you to determine the isentropic efficiency of the compressor and turbine. For the compressor, since you already have the ideal power input and also the actual power input, then you can use this relation and times with 100 to get the isentropic efficiency in percentage. Okay, so once you substitute, you calculate, and then you will get 82% for the isentropic efficiency of the compressor. Alright, so next, how we can determine the isentropic efficiency for the turbine, because we doesn't have any information about state 4 leaving the turbine. So the first one, you can find the T4S by using this isentropic relation. So we have T4S over T3 equal to P4 over P3, K minus 1 divided with K. And once you substitute all the necessary values, then you can get the value of T4S is 772.9 Kelvin. So you already have the value for the T3. You already have the value for the Cp, you already have the value for the m dot, the mass flow rate, and you already have the value for the T4S. Now you can determine the power output, the ideal power output by the turbine. Right. So next we want to find what is the actual power output from the turbine. So we already have the power net out that is being given from this question. Power net out equal to 45 megawatt, and we also have determined the actual power input by the compressor, 45,225 kilowatt, based on the formula power net out equal to power out minus power in. And then we can determine the actual power output by the turbine. So we're going to use the 45 megawatt, which is the power net out, and also we are going to use the calculated actual power in by the compressor, and we are going to get the value of 90,225 kilowatt. So from there we already have the actual power output, and we have the ideal power output that have been calculated previously. Now you can determine the isentropic efficiency of the turbine. So please do remember, please look at your appendix also. The isentropic efficiency for the turbine will be the actual over the ideal, and for the compressor will be the ideal over the actual. Please ensure that you are using the correct formula to determine this isentropic efficiency for the specific devices. Alright, so for the isentropic efficiency of the turbine, you're going to get 95.4%. Okay, next, item C, they requires you to determine the thermal efficiency of the cycle. So we know that the thermal efficiency, if you look at your appendix, it will be given by power net out divided with heat transfer in, okay, Q dot in. So please ensure, okay, if let's say you are using kilojoule per second, so for the Q dot in also you need to use the same unit. Okay, you need to make sure that the unit is homogeneous, and please also do know that joule per second is referring to watt. Okay, so for this will be the kilowatt. Alright, so for you to get the kilowatt, definitely it's going to be enthalpy times with the mass flow rate, and for the enthalpy of an ideal gas is CPT. Alright, so you have the term CPT over here, and definitely you need to times with the mass flow rate. Okay, so for the Q dot in, you can determine easily since you have the informations on the T3 and also T2A, and then you can substitute into the thermal efficiency formula. Then you are going to get the thermal efficiency for the cycle is 37.5. Alright, so for item D, item D is for you to determine the new thermal efficiency in percentage if an ideal regenerator with 100% effectiveness is added to the plant. Right, so if you draw the Brayton cycle with regenerator on a TS diagram, it will look like this. Okay, so we have state 2, state 1 entering your compressor, state 2 is leaving your compressor and entering your combustion chamber. Sorry, that will be if you are referring to the if you are referring to the simple Brayton cycle. So once you have the regenerator, state 1 is entering your compressor, state 2 is leaving your compressor and entering your regenerator. Okay, state 5 is leaving your regenerator and entering your combustion chamber. State 3 is leaving your combustion chamber and entering your turbine. And state 4 is leaving your turbine and entering the regenerator. And then state 6 is leaving your regenerator, and supposedly it's going to be exhausted to the ambient. Alright, so for 100% effectiveness, most likely the temperature at state 5 will be the same as temperature at state T4A. Okay, at state 4A, the actual state leaving our turbine. Okay, or if let's say you want to do it in, you want to prove it by using a simple calculation, then you can always use the formula for effectiveness. Okay, but for our case, definitely, since the effectiveness is 100% 1, so later you're going to get T5 will have the same value as T4A. Okay, maybe you can try to prove it by using this effectiveness formula. Alright, so since we doesn't have the informations of the T4A, but we already know, okay, we already know the the T4S, T3. So by using the isentropic efficiency of the turbine, which you already have calculated over here, 95.4. So if you convert it into a normal representation, will be equal to 0.954. Okay, so from there you will get the T4A is 801.7 Kelvin. So we know that T4A will be equal to T5. So for the Q dot in, the new Q dot in, from the formula of m dot times Cp times T3 minus T5, and we know that T5 is equal to T4A, then you substitute all the required values, then you are going to get the thermal efficiency. The new thermal efficiency is 49.89%. Okay, so if we look into these two, thermal efficiency, the simple Brayton cycle, and also the Brayton cycle with regenerator, we can say that the Brayton cycle with regenerator having higher thermal efficiency as compared to the simple Brayton cycle. Okay, that's all from me. I wish you all good luck for your final examination. Assalamualaikum and good day.